Hi, everyone. We'll get started in just a couple minutes. All right, let's go ahead and get started. Welcome to our webinar, everyone. Today, we're going to discuss how to conduct and interpret tests of differences, primarily t-tests. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. If you have any questions, you can type them into the chat box. At the end of the session, I will be doing a Q&A. And my colleague Brittany will be assisting with questions during the webinar. If you have any questions about the services we provide, she will be providing some hyperlinks. So let's go ahead and dive in. It shouldn't be too long of a session as there aren't too many t-tests. There are only 3 different types. So I'll discuss some services that we provide at our company, and then we'll discuss t-tests, how to set up the data set, how to conduct them, what assumptions to check, and how to interpret them. We'll do an Intellectus demonstration. Intellectus is our company software that is used for crunching numbers and presenting analyses. And it gives you an APA write-up and interpretation of your findings. Pretty cool. And then we'll conclude with a summary and Q&A session. So on this slide, you can see all the services that our company provides. We have literature review specialists and methodologists, both quantitative and qualitative. So if you need help framing your research questions or developing a purpose and problem statement, maybe finding a gap in the literature, and going all the way to interpretation of the findings and running your analyses. We do assist with every part of the dissertation journey, as well as if you're working on a thesis or a journal publication. If you have any questions, you can give us a call at 727-442-4290. So what is a t-test? In general, a t-test is used when testing for differences in a variable. There are 3 types of t-tests. First type we will discuss here is an independent sample t-test. This is used when you're testing for differences in a continuous variable between 2 independent groups. So what's a continuous variable? A continuous variable is a variable that falls on a scale or a continuum. So, GPA or test scores or composite scores that are generated from a survey instrument. Those are all generally considered continuous. So you need to have one continuous dependent variable, and you need to have an independent grouping variable that is dichotomous. Dichotomous means 2 discrete groups, 2 independent groups. So examples like gender, you have males and females, or groups in an experimental study. That's a very popular type of independent variable to use for a t-test. So if you had a treatment and a control group, that's when you would run an independent t-test. So when you have this set up and your research questions are finalized, and you know that a t-test is the best option, you then want to review the assumptions that you should verify. So I provided a hyperlink here for Statistics Layered, which is a very popular website used today that kind of teaches you how to run analyses in SPSS. So it explains how you should set up your data and what assumptions you need to verify. For a t-test, you can see that there are several assumptions. There are 6 of them on this website. depending on what reference or citation you read, you might see different assumptions or a different number of assumptions. I think 6 for a t-test, this is on the high end. The most important things to check are normality and homogeneity of variance. A couple of the earlier assumptions are just making sure that your variables are the correct measurement. You know, your dependent variable needs to be continuous. That's fundamental. To run a t-test, you need to have a continuous dependent variable. And then your independent needs to have 2 or more groups, or just 2 groups exclusively. If you're doing 3 or more groups, then you run an ANOVA. And we'll be doing a webinar on ANOVAs in the future. But t-tests are nice and simple, just a 2-group comparison. So the key assumptions I usually check are these 2. And then I check for normality and homogeneity of variance. And we'll talk about those assumptions a little bit later in the webinar. Once you have the data, you can upload it into our software and you can run it. And I will demonstrate that shortly. What's the second type of t-test? We have a paired sample t-test, which is also called a dependent t-test. I've seen it used both ways. This is used when you're testing for differences in a matched continuous variable between 2 points in time. So the assumption here is that you're doing a pre-test and a post-test. Same participants that take your pre-test, they come back and they take a post-test after an intervention or after some activity that happens in the middle. So this is when you do a paired sample t-test. And for this, you just need to have one matched dependent variable that's a continuous measurement, and it's measured at 2 points in time. Again, you can check out the statistics layered website, and you can see the assumptions that are verified for this one. And very similar, there should be fewer assumptions as there are no groups. Notice that we don't have an independent group like gender or treatment and control. This is generally looking at a collective sample. So you just need a dependent variable that is continuous. Your independent variable is essentially the matching of your data, meaning you have a pre-test and a post-test and the same participants are coming back that took the pre-test. Outliers are also something that should be checked for both independent and dependent. Really, regardless of what analysis you're running, you want to check for outliers before you do anything. So I don't even consider that really an assumption. It's just something you do as soon as you gather data. And you can do that with box plots and scatter plots or z-scores. And then the final assumption is normality. Okay, so there are many ways to check for normality, and we will discuss that shortly. Okay, and that is the next slide, normality. Normality is ensuring that your data follows a bell-shaped distribution. So everyone here, I'm sure, has seen a bell-shaped curve, and that's one of the prerequisites or assumptions for running parametric analyses like t-tests and regressions and ANOVAs. So there are many ways to check for normality, depending on what reference you read. And this is really, I would say, committee specific thing. If your committee is quantitative or they focus on quantitative dissertations, they probably have a preference for what method to use. And that goes for assumption testing as well. You know, the statistics layered website I showed 6 assumptions for a t-test, for an independent t-test, but your committee might not want all those assumptions. They may only want to examine a couple of them. So it's important to check with the guidelines for your school. So you can use tests of significance to check for normality, like a Shapiro-Wilk or Kolmogorov-Smirnov test. You can also look at descriptives like skewness and kurtosis to tell you if the data are skewed and deviate from normality. And you can also use scatter plots and histograms. So there's the objective testing method and there's the visual interpretation using scatter plots or histograms. If the data don't follow a normal distribution, Usually you need to make an adjustment to the data, and you can either transform the data, you can try and change it to a logarithmic or a cubic function that's a little more complex. I try to avoid transformations. Instead, I run non-parametric techniques. And for every parametric test, like a t-test, there is a non-parametric equivalent to that test. And we'll discuss that in just a bit. The alternative here is if you have a large sample size, generally greater than 50 cases, you can justify normality not being supported with the sample size. And this is called the central limit theorem. And it basically states that the higher your sample size, the more it resembles the true population, which is in turn a normal distribution. So the larger the sample size, the better with any statistic. Okay, so as we discussed, every parametric test has a non-parametric alternative. I shouldn't say every test, most of them do. So for an independent t-test, again, if you're looking for differences in a variable between two groups, the non-parametric alternative to that is called a Mann-Whitney U-test. And this is used when you either have a non-normal continuous variable. So if you evaluate for normality and the assumption's not met, then you can run a Mann-Whitney as a backup. The alternative is if you have an ordinal dependent variable as opposed to a continuous variable. So instead of a number or like GPA or grade, if your dependent variable was something like education, high school, bachelor's, master's, PhD, that's more of an ordinal variable. That's when you can use a Mann-Whitney test. You don't want to use a t-test for an ordinal variable. You need to have a numeric continuous variable. As far as the paired t-test, the non-parametric alternative to this is a Wilcoxon signed rank test. So very similar to the independent and Mann-Whitney test, a Wilcoxon signed rank test can be used if you check for normality on your dependent variable and the assumption is violated, then you can run this Wilcoxon test as a backup. And the same principle applies if you have an ordinal dependent variable like education or just a Likert scale item, going from strongly agree to strongly disagree. You can use that ordinal dependent variable in a Wilcoxon signed rank test. Final example, which is really short, there isn't really much to this, is a one-sample t-test. And this tests for differences between a continuous variable, so perhaps a measure that you collect, GPA, grade, test score, and if you want to compare that variable to a specified value, that's when you can run a one-sample t-test. So if you had literature that said maybe the average test score was an 86 for a particular test, and you want to compare that to your sample, that's when you run a one-sample t-test. Okay, so collectively, you first want to frame your research questions. Are you looking for differences between groups, or are you testing for differences over time? If you're testing between groups and specifically only two groups, you run an independent t-test. If you're testing for 2 points in time, then you do a paired t-test. When you extend that, once you add 3 groups or 3 time periods, that's when you go into ANOVAs, which are a little more complex, but the same principle applies. You're testing for differences between those 3 or more groups, or you're testing for differences over time. If you had maybe a baseline, a pre-test, post-test, and a follow-up, and not just a pre-test, post-test, that's when you can do a repeated measures ANOVA. And then once you collect your data, you can use Intellectus statistics to analyze the data and present the interpretation. So let's take a look at Intellectus. Here we have Intellectus, and basically you can upload a data file. And once that data file is uploaded, it looks like an Excel spreadsheet basically, or more similar to SPSS, I suppose. And in this spreadsheet, this is just a sample data set I found online, and it was measuring pre and post for participants. And this was a measure of a 5K completion time. So how many minutes did it take to complete a 5K? I had a pre-test, and then a fitness intervention was conducted, and that post-test, the 5K time was measured again. So we can see how we could run a combination of analyses here. We could run a paired t-test to see was there a difference between time 1 and time 2, and note how the data are matched. So I don't have a separate row for the pre-test and post-test. This one individual, one participant, needs to have their pre-test and post-test on the same exact row. And then we could also test for differences by gender. So if we wanted to say, was there a difference in 5K completion time between males and females? That's when we can run an independent t-test. Okay, and you can see all the data management functions we have in here. I did discuss transformation earlier, that if normality is not supported, you can try different distributions that could fix the data and make it resemble a bell-shaped curve. We have removal of outliers as a function. So if you remove univariate outliers on these, it's going to create a new copy of those variables. And if there are outliers, they will be removed. It looks like we don't have any outliers in this case. You can reverse code items if you have a Likert scale that is negatively phrased. You can use reverse coding, and we have imputation, which predicts missing responses. Okay, and then we have several plots that you can generate. For instance, if you wanted to see time by gender, time to complete the 5K by gender, you can do a profile plot. Looks like this, and right away we can see that there does appear to be some differences by gender and potentially over time. Okay, and then in this window we can see all the different analyses that you can conduct. And as far as assumption testing, you can see we have the normality checks, another check for outliers, Levine's test for homogeneity of variance, and then various analyses. Today, we're focusing on t-tests, and I'll come back to this in just a second. Let me show you the methodology information we have in here. So first we have a decision tree. So if you're kind of at the beginning of the process and you're trying to figure out what is the best analysis to run, and you've generated your research questions, I suppose you have the purpose statement and research questions laid out, then you can use the decision tree here to figure out what analysis you need to run. So say we want to explore for differences between groups. Do you have more than one dependent variable? No. Do you have any covariates? No. Do you have more than one independent variable? No. Does your independent variable have more than 2 levels? No. And you can see it goes all the way down the decision tree and tells us that a t-test is probably the best option here. Data analysis plans will present information for the methodology. First, it gives you a sample research question and hypotheses, and then it kind of dives into how the t-test is conducted, why it's conducted, what is the interpretation, and we have references at the bottom. And then you can see power analyses as well, in which you can determine what is the minimum sample size to collect when you want to run a t-test. So we use GPower. GPower was the software that was used to replicate the power analysis findings here. So for example, if we're doing an independent t-test, I just click independent sample t-test, it will give you 3 write-ups for a power analysis based on what effect size you are using. So if you use a large effect size, that you're generally going to need a smaller sample. The most conventional effect size to go with is a medium effect size. And this is used if you don't have literature, from a prior study that says you should use a small effect size or a large effect size for this study. If someone in the past suggested use a different effect size, then you can go with a large or small. Otherwise, medium is always a safe bet. So we can see that we need 128 participants for a independent t-test, which would mean, ideally, that would mean you have 64 participants in each group. And then for a paired t-test, we can see going with a medium effect size, we need 34 participants ideally. So that would be 34 pre-test, the interventions conducted, and then 34, the same 34 returned post-test. So it's better to aim higher. 34 isn't the absolute number. It's better to gain more if you can, because you have to account for attrition, people not returning for the post-test or maybe incomplete responses. So you want to aim higher if possible. Okay, so as far as the analyses, we're going to use this spreadsheet here, and we can test for differences between time 1 and time 2. That is a paired t-test. So we'll go to analyses, t-tests, and then paired sample t-test. Variable 1 will be time 1. Variable 2 will be time 2. Okay, and then it runs. And first it checks for normality. You can see right here. And the assumption of normality was not supported, meaning that the time 1 and time 2 values are not following a bell-shaped distribution. The normality wasn't supported. Regardless, it still runs the t-test. And we can see here that between time 1 and time 2, the amount of time dropped by about 3 minutes. And this p-value here tells us that we had a significant difference over time. Then we have the effect size at the end, Cohen's d, that pretty much tells you what is the strength of the difference over time. And then we have a bar chart at the bottom. Okay, so because normality was not supported here, this is a case where you might want to run a backup. And we talked about the non-parametric alternatives right here. So if normality was violated, as it was for the paired t-test, we will run a Wilcoxon sign rank as a backup. Okay, so that is a non-parametric, which is under this menu, and then Wilcoxon sign rank test, and the exact same process as we did before, time 1 and time 2. Calculate. And again, we do see significant differences. So Wilcoxon uses a different formula. It uses medians as opposed to means. You can see up here, we used mean values. So essentially the average at time 1 and average at time 2. Down here, we are using the median at time 1 and median at time 2. And the findings were still significant. Our p-value, as I hover over this term, it is significant because it's below 0.05. So basically, we ran the t-test. We found that it was significant. Because normality wasn't supported, we ran a backup to the t-test, and it was still significant. So it gives you more validity in the findings. Now we could test for differences in time by gender, just to illustrate an independent t-test. Gender only has 2 possibilities, male and female. So it's a good example to run an independent t-test. You need to put in one of the time periods. I'll just put in time 2. And we can look at gender as our independent variable. Okay, so for an independent t-test, there are 2 primary assumptions to check. The first one is that normality is supported again, and in this case, it was not. So time 2 did not meet the assumption for males or for females. So we should consider running a backup test after we look at this t-test. Homogeneity of variance is making sure that the spread of the times are approximately equal between males and females. So it's essentially looking at the spread or the standard deviation down here. And this p-value tells us that we have a difference or a significant difference in the times between males and females for the standard deviations. So that assumption was violated as well. So we should really run a backup after doing this t-test. What we can see is that the average male time was 19 minutes, and the average female time was 38 minutes. And the p-value tells us that the significant difference existed between males and females. Okay, so now to run the backup for a independent t-test is a Mann-Whitney test. That's covering this slide here. We ran a t-test. The assumptions were not supported. So we should run this backup just to ensure that we are not missing something. So we'll go to non-parametrics, Mann-Whitney test. The dependent variable will be time 2, and the independent will be gender. Okay, and again, in this case, we use mean ranks. It uses medians and mean ranks for this one, and we still do see significant differences with males having a significantly lower time than females. And the last example is a one-sample t-test. So this is usually something where you need literature to support what you're running. For example, if we wanted to see if time 2, if the average for time 2 was different than what a prior study found, say a previous study found the average was 23 minutes. So then we can go into a one-sample t-test. The dependent variable will be either of these. So I'll just do time 2. And then the test value is specifically the value you want to compare it to, and 23. Okay, and then we can see here that the average for time 2 was 27.49, and we are comparing that average to the population mean, which is 23. And ultimately, we found that there was a significant difference between our sample for time 2 and the population mean, which was 23. Okay, so that pretty much covers Intellectus. Once you're done and you've run your analyses, you can download the document at the bottom right here, and that is going to generate a Microsoft Word document. And then it will give you a table of contents for what was run, and then it will go through the analyses and give you interpretation. And then there's a glossary of terms at the bottom for every term, every statistical term that was used in the chapter. Okay, so that pretty much covers the webinar for today. Do we have any questions? I do see we have some comments. Let me check those out. Okay. Question from Navisan. Is it possible to include a Likert scale data in a regression model? Yeah, it is a little bit different than the topic today, but yes, what you have to do is dummy code a Likert scale. And I think I talked about that during the previous webinar briefly, but look into dummy coding. You'll have to assign a reference group. So for instance, if you're using strongly agree to strongly disagree, you can make strongly disagree your reference group, and then you have to create 4 new variables. One that would be like disagree versus strongly disagree, then neutral versus strongly disagree, then strongly agree versus strongly disagree. You have to pick one of those Likert categories to be the reference group. Okay, so a question from Teresa. So for Likert scale scores, you must use Mann-Whitney for normalcy, and can an independent sample t-test be run? It depends if you're using a single Likert scale item or if you're using a composite score. A composite score is generated through an average of Likert scale items. So for instance, the job satisfaction survey has 10 items that are measured on a Likert scale. Once you take an average of those 10 items, you can have decimals as possibilities. And at that point, it is continuous. So you could run an independent t-test. But if you're using just one of those questions on the job satisfaction survey, just one Likert scale item, then you should probably run a Mann-Whitney test because it is considered ordinal. That's been a point of debate for many years about whether Likert scales are continuous or ordinal. I think there's far more support that they are ordinal. So I would use non-parametrics in that case. Navson looks like you had a question about the software. Brittany included a hyperlink there for Intellectus. And yes, Teresa, SPSS data can be transferred. Let me illustrate this. Once you are on the home page of Intellectus, you can upload a data file and you can see all the different types of files you can upload. We have CSV, Excel files, SAV is SPSS. And then we have SAS and Stata as well. But SAV is a very common SPSS format. Yep, you're welcome. Okay, we have a question from Aruj for mediation and moderation analysis using latent variables. Which tests would you use? You probably need to run structural equation modeling. Going to advanced over here. And we do have mediation and moderation, but you can't put latent variables in this. These are just observed variables. You would most likely need to do path modeling. It's under path modeling. So either a path analysis in which you can develop your specific paths for mediation and moderation, or you could use structural equation modeling. Those are both good options. Do you correct grammar for the thesis? If so, at what cost? That's more of an APA editing service, and we do provide that. So you'll want to first speak with Janine, and she can guide you in the right direction. All right, do we have any other questions? We will be sending everyone a copy of the PowerPoint and the webinar as well. Question from Aruj, can you specify which method is preferred? OLS, ordinary least squares regression, or structural equation modeling? Well, with latent variables, you probably need to run structural equation modeling. OLS, as far as I know, it only uses observed variables and not latent variables. So if you only have observed variables, I would do OLS. If you have latent variables, then you can do structural equation modeling. Yep, you're welcome. Do we have any additional questions? Anything about the software, t-tests, what analyses to run? All right, sounds good. Thanks for joining, everyone. Come join us for the future webinars. I'm sure you all have seen this link already. It's probably how you joined this one. but just in case, on our company website, you can go to webinars up here. And for one, you can watch prior webinars we've done. This will have the recording. And then you can also see what is upcoming. So it looks like tomorrow we'll be doing a quantitative results chapter webinar. And I believe my colleague David will be doing that one. And then we have an introduction chapter webinar, which will be done by my colleague Tom. So come join us for those future webinars and let us know if you have any questions. Have a great day.